This video is part of a series on the xv6 operating system kernel. In an earlier video, I described the inode system and talked about the general organization of the file fs.c. I talked about the data structures, and I gave an overview of all of the functions in that file. In the previous video to this video, I started walking through the code of the functions that are in fs.c, and in this video, I will finish walking through those functions. Let me just put on the screen for a visual reference what functions were covered in the previous video. So we covered all of these functions, and here are some more that we covered. I will start with bmap in this video, but in the previous video I covered itrunc and stat_i. After I talk about bmap, I will go ahead and talk about the remaining functions, starting with read_i and so on. And as I said, we are working toward the name I function, and I will end by talking about the name I function, which is the function that has passed a pointer to a string that contains a path, and will find that file on the disk and read an inode into the in-memory cache and return a pointer to that. So let's get started. From time to time, we want to read data from or write data to a file, and we need to know where on disk that data is stored. So which block number on disk do we need to read or write to get the data? And that's the function of this bmap function. It's passed a file, or more precisely a pointer to some inode describing a file, as well as the block number relative to the beginning of the file. So let's say we want to write some bytes in, well, let's say the 7th block in the file. We need to convert that 7 block number into the actual block number on disk. Return the disk block address of the nth block in the file. And if that block has not been allocated to the file, then this function will allocate and zero a new block. So looking at the picture here, what we are going to do, let's say we want to get the 7th block, we'll need to go to the cache inode. Well, let me use this picture over here because it's got the indirect block. And if it's in one of the first 12 blocks, we just need to access the inode and get the block number and find out where on disk that block is stored. If it's greater than 12 here, if it's 12 or greater, we need to access the indirect block and get the block number from the indirect array. So that's what we are doing here. First, we're asking whether the block number that we're looking for is less than, well, 12. That is, if it's 0 through 11. In that case, we can use one of the direct pointers. So we are going to look into the inode and the array and get the element from that array and save it and then return it. Okay, if that array contains a 0 pointer, then that block hasn't been allocated. So we need to call balloc. We will allocate or find a free block and set it to all zeros and return the block number on disk, which we will then store into the array so that it will be there in the future. And in either case, we return the block number. However, if the block that we're looking for is 12 or greater, then we are going to need to follow this pointer and look in the indirect block. So for example, if we're looking for block number 14, well, this is 12, 13, 14. It's this one. We need to take the block number 14 and subtract off these first 12 to get an index into this array. That is, we need the index of 2. So that's what's happening in this line here. We're subtracting off 12 from the block number, and now we've got an index that's between 0 and 255, or at least we hope it is. The first thing we do is check to make sure that our index is not larger than 255, and if it is, well, we've tried to access a block that is beyond the maximum file size. That should have been checked by whoever calls this function, and if not, we issue a panic. So then we need to load the indirect block, and we then go to the array, and this is the last element of the array, and ask whether it's 0 or not. If it is 0, then we need to allocate the block of indirect pointers. So here we allocate that indirect block and set it all to zeros, and we save the block number of the indirect block in the array. So we're allocating this block here and saving a pointer in this element here, and that happens here. And in either case, we get to the address of the indirect block, and here we are reading the indirect block into some buffer and setting A to point to where that data is in that buffer. So that's the beginning of this array. And then we're using our value here to index into that array, and we are saving the element. So that's the block number that we're interested in. And if it's null, then that block hasn't been allocated. So we have to call balloc again to allocate a block and set it to 0. And we will store the block address of the freshly allocated block into the array. And we need to update the indirect block if we have modified it. So that's where we have the log right here. But otherwise, we don't need to update the indirect block. We just use the address that we retrieved and return that. So here we are releasing the indirect block, or more precisely, releasing the buffer that contains the block of indirect pointers. Now, you can see that we are modifying the inode here. Okay, we could be modifying the array directly either here or here. And so if we are modifying it, we need to update the inode on disk. So that's the responsibility of the caller of bmap. So let's keep that in mind. At some point, we're going to want to transfer bytes from the file to memory, and that's the purpose of the read-I function. So it's going to read data from the file that's described by the inode pointed to by IP. We're going to get the data from this offset within the file, and we're going to transfer in bytes. We're going to move those into memory, and the address that we're going to move them to is given by the destination argument here. That could either be a virtual address or a physical address, and that's determined by this argument here. If this argument is a 1, then the destination address is an address in the virtual address space of the currently executing process. If this is 0, then destination is a physical address in the kernel address space. We begin with a couple of checks. First, if the offset is beyond the end of the file, then we return 0. By the way, this function returns the number of bytes successfully transferred. This test here is written in an odd way. If you subtract offset from both sides, you see that it's really just checking to see whether the number of bytes that we want to transfer is less than 0. And if it is, again, we return 0. Offset may be within the file, but the extent of the amount of data that we're transferring may go beyond the end of the file. And if that's the case, then we need to reduce n so that we only transfer as many bytes as the file has. So here we compute the number of bytes between the offset and the end of the file, and that is our new n. So the n bytes that we want to transfer can be spread over several blocks in the file, and we need to read each block individually and get the bytes out of that block. And we'll call bread a number of times, and for each one we'll transfer using this either copy out function. So this loop will transfer a number of bytes each time, and then it will finally terminate and return the total number of bytes transferred. So we start total at 0, and we end when we've transferred n bytes, and then we return the number of bytes that we've transferred. So the first thing we need to do is figure out for this particular chunk, for the next chunk, where it is in the file and where it is on the disk. So the current offset from which we're getting data is given by offset. And as we go through, we'll advance offset and we'll advance the destination pointer as we do each chunk. We'll compute the number of bytes we're going to transfer here, that's m, and increment the source, the offset within the file, as well as the destination pointer and the number of bytes transferred. So we take the offset where we're at right now and figure out what block it's in. So we compute the block number that contains offset right here and call bmap. Bmap will map this block number, which is relative to the beginning of the file, into a block number on the disk. And then we call bread to read that into a buffer, which is pointed to by this buffer pointer here. Now we figure out how many bytes we want to transfer in the next step. And so we don't want to go over the end of this block. We don't want to go past the end of this block. So that's what we do here. We take the offset and see how much is left in this particular block with this expression here. And we don't want to transfer bytes beyond what we're supposed to transfer. So we look at how many bytes we've transferred so far and subtract that from m, and that's how many bytes we have left to transfer total. And we take the minimum of those two, and that will be the number of bytes we're going to transfer. So then we call either copy out, and we covered that earlier, but basically it's passed a source address here, a number of bytes to copy, and a destination address, and then a flag to tell whether those bytes will be copied into a user's virtual address space or into the kernel space, into a physical memory. So that's just the parameter that we had up here. Okay, and we are copying m bytes. And where are we copying them from? Well, we're copying, here's where the data is in the buffer, and we look at the offset and we figure out where that is. So we offset into the buffer's data, and that's where we begin copying our m bytes, and destinations where we copy them to. And if anything goes wrong, this function will return a -1, and we immediately abort. That could be if the destination address is not actually in the user's virtual address space. It's not an allocated page. For example, that could cause a problem. And if that's the case, then we immediately release the buffer and return a -1 and break out of here. So we set total to -1 and then return that. But if the copy is okay, then we just continue. We release the buffer that we allocated here and then iterate and do the next chunk. We just copied m bytes, so we add m to the total bytes we've copied so far, as well as from the source address within the file, that is the offset, and the destination address where the bytes are being copied to. Now, one thing I want to point out is we're calling bmap here. And as I mentioned earlier, bmap can modify the inodes in memory. If the data is not allocated in the file, it will allocate it. So it may allocate new blocks and add them to the file. And that will modify the inode. And it is the responsibility of the caller of bmap to write that modified inode back to the disk. And that doesn't happen here. And I think that is a bona fide bug in this code. But you know, maybe there's something I don't see. Yes, there definitely is something that I didn't see at first. After looking at this code, I've come to believe that it's just fine as it is. In Unix, we have the fs.c system call. And if this is a file here, you can use fs.c to seek to a certain point beyond the current end of the file, and then you can do a write. The POSIX specification says that the bytes in between here that were never actually written will be initialized or assumed to be 0, so that if later you go back and you do a read in this region here, the read system call should return the 0 bytes that were supposed to be there. I made the assumption that xv6 works the same way and that you could have these gaps like this, but in fact, that's not the case. In xv6, there is no fseek system call, so it's impossible to do something like this. You cannot start writing beyond the end of the file. In fact, with xv6, writing will always start at position 0. I suppose that if you don't want to start writing at position 0, you will have to do a bunch of reads to get to whichever position you'd like to start writing at. So with xv6, the blocks in the file are always allocated. So let's assume that we have a file and it goes from this point up to some size. And so here's the file in blue. And what this means is that all the blocks, and each one of these is supposed to be a block, will be allocated. And the last block might not be fully used, but all the blocks in here will be allocated, and none of the blocks beyond this point will be allocated. So that means that the read-I system call, when it calls bmap, will only be reading blocks that are already in the file, and that means there will never be an update to the inode. So there's no reason or no necessity to call the iUpdate function like there is in write, as we will see in a second. This points out that a lot of times we make assumptions about the code that we are either reading or writing, and these assumptions are often below the level of consciousness. We have these assumptions in the back of our mind, but they may not be clearly articulated. If we want to prove in a mathematically strict way that the code is correct, then we may be required to make all of our assumptions explicit and write them down. Doing that, proving a program is correct and making all these assumptions explicit, is an excellent way to find bugs. But with the xv6 operating system kernel, we are not going to go into that level of analysis. Okay, so let's move on to the write-I function. To write data to a file, we have the write-I function. So it will write data to the file that's described by this inode, and the caller must hold a lock on that inode. The data is coming from memory at the location given by this argument, source, and that can either be a virtual address in the address space of the currently running process, or it can be a physical address in kernel space as determined by this argument here. We are placing the data in the file at the location given by this offset here, and we'll be copying n bytes. This function will return the number of bytes successfully written, and it might be less than the requested n if there's an error of some kind. So it's very similar, the code is very similar to the read-I function. We start off by asking whether the offset is beyond the end of the file, and if so, we return -1 in this case. And we also ask whether the number of bytes to be transferred is less than 0, and again, that's considered to be an error, so we return -1. And we also ask whether we will be going beyond the maximum file size. So max file is the maximum number of blocks in a file times the block size. And if offset plus n is greater than that, then we've got to return an error indication. The loop here is roughly the same as we saw in read-I. We're going to break the transfer into a number of chunks of size m. And so we start with the total number of bytes transferred so far, that's 0, and we'll stop when we've transferred all n bytes, and we'll ultimately return this total number. And we compute the number of bytes we're going to transfer as m, and in each iteration of the loop, we'll be adding m to the offset in the file that we're writing to, as well as the source address where we're getting the bytes from, and we'll increment the total number of bytes that we've written so far by m. And again, this is exactly the same as in read-I. We take the current offset in the file, figure out what block it's in, call bmap to determine the block number on disk, and then call bread to get that block into a buffer pointed to by bp. Then we compute m. Here we are limiting n. If we are going past the total number of bytes we need to write, then we stop there. And so n minus total is the number of bytes left to write, so we don't want to write any more bytes than that. And we also don't want to go beyond the end of this block, so here we compute how many bytes are left from offset in this particular block. And then we use the either copy in function, which will copy from this location in memory, source. which is either in virtual address space or kernel address space, as given by this parameter here. And we'll copy m bytes. And where will we be copying them to? Well, we've read in the buffer that contains the range of bytes that we are going to be writing to. And so here we compute where that is. So here's the data in the buffer, and here's the offset within that data, and that's where we're moving data to. And after we copy the data from memory to the buffer, we need to write this buffer back to back to the file. So here we invoke the logWrite function to do that, and then we release the buffer. If the either copy-in function has a problem, it will return -1, and we then release the buffer and break. Now we need to update the size field. So here we are updating the size attribute of this file. If the offset that we're at now, after we end this loop, exceeds the current size of the file, then we need to grow the file, or at least make a note that the file has already grown. bmap will be the function that actually adds records or adds blocks to the file. So write the inode back to the disk, even if the size didn't change, because the loop above might have called bmap, well, it did call bmap, and that bmap might have added a new block to the file and therefore modified the array of block pointers. So we do call iUpdate here, and finally we return the total number of bytes transferred. Next, let's take a look at the directory lookup function. It's passed a directory, or more precisely, a pointer to a cached copy of the inode for that directory file, and a pointer to a string. And it looks that name up in the directory, and if it finds it, it allocates a cached version of the inode for that file and returns a pointer to that. It also has the capability of returning the offset within the directory at which it found this name. And that could be useful if, for example, we want to delete an entry from a directory. So let me remind you what the directories look like. We have this directory entry structure that's 16 bytes in length. It has two fields. The inum field is only 2 bytes, and it has the inumber of the file. And then we have 14 bytes for the name of the file. If the name is shorter than 14 bytes, it will be followed by a null byte. And a directory is just a file that contains an array of these. So here's an example directory. Some of the entries will have an inumber of 0, and those are essentially unused entries in the directory. So this directory seems to have 3 files in it, and so we have the file name. If it's shorter than 14 characters, it is followed by a null byte, and if it is 14 characters, then there is no null byte. But in any case, there's the inumber that's associated with these names. For the ones that are 0, we don't really care about what characters we have for the name. Okay, so what do we do in this function? First of all, we check the file that we're passed, the directory, to make sure that its type is in fact a directory, and if not, there's a serious problem. Then we're going to go through the file. So offset will start at 0, and it will be incremented by the size of these directory entries. So we have this local variable called DE, directory entry, and that's a 16-byte value. And so we're going to increment the offset in units of 16. So here, here, here. And we're going to end when we get to the end of this file, the size of the directory file itself. And for each iteration of the loop, what we're going to do is we're going to call the readi function. So we're going to read from this directory file, okay? And where are we going to read? We're going to read from this offset, and we're going to read, well, it's 16. The directory entry is 16. We're going to read 16 bytes, and we're going to place those bytes in this DE variable here. And we make sure that we got 16 bytes, and if we didn't, well, something's really wrong, so we panic. If the inumber of this directory entry is 0, then we skip and go to the next one. with a continue. Otherwise, we compare the name that we're passed, okay, this string here, with the name in the directory entry and see whether they are equal. So at this point, let me look at this name compare, okay? That's a little function here that is passed two strings, and it uses string in compare to compare up to 14 characters. Well, it compares up to the first null byte, and in any case, no more than 14 bytes. And so if the name is equal, then we have found it, okay? If the two names are equal, then we have the entry that we're looking for. And so we grab the I number that's associated with it. Also, if this poff argument is non-null, then we store the current offset of this directory entry in the variable that's pointed to here. And once we've gotten the I number for this entry, we then call iget. Recall that iget will allocate an inode in the cache of inodes, and it will initialize it with the appropriate device and I number. And from then on, we can lock it if we want to, but at least we've got a pointer to the inode cached in memory. If this loop goes all the way through and ultimately reaches the size of the directory file and still hasn't found a match, then we return 0 to indicate that we haven't found anything. So next we have the directory link function, which is used to add an entry to a directory. It's passed dp, which is a pointer to the inode for the directory, as well as the name and I number to be added to the directory. It will return 0 if everything's okay, and -1 if there's a problem. The first thing it does is it calls directory lookup to determine whether this name is already in the directory. If it finds something, then it will set IP to point to the inode for that file. It will call iget to do that within directory lookup. If that's the case, then, well, that's a problem. We need to return -1, but we are not interested in the file that we've already found, so we call iput to undo the iget, if you will. Then we look for an empty directory entry. So we're going to look through the directory file, starting with offset 0 and incrementing by the size of these directory entries. And we're going to stop when we get to the size of the file after we've looked at them all. And for each offset, we will call readi to get from the directory file 16 bytes, and we'll transfer it from the current offset within the file to this DE variable. This directory entry variable here is a local variable of 16 bytes, and that's in physical memory, not virtual address space, so that's the flag is 0 here for that. And if for some reason we're unable to transfer the data, unable to transfer a full 16 bytes, then there's something dreadfully the matter, and we panic. But otherwise, we then check the directory entry's I number to determine whether it's free. If it's 0, then we found a spot in the directory that we can use, and we break with that offset. Otherwise, we go all the way up to the end of the file, and offset will be equal to the size of the file, because the size of the directories is a multiple of 16. And in either case, we are now ready to create the directory entry and write it to the file. So here we are copying the name into the directory entry variable, and we copy it up to 14 characters, and we copy the I number into the directory entry, and then we write that directory entry. So we're writing it, here's where we're writing from, and this is an address in kernel space, so the flag is 0, and we're writing to the offset. This could be the offset of an entry that is unused, or it could be an offset beyond the end of the file. And it doesn't matter which, this will grow the file if necessary. And so we write 16 bytes, that's the size of the directory entry. If there's anything wrong, we panic. But otherwise we're done, and we return 0 to indicate success. In order to open a file, we need to be able to deal with path names. The next function we want to look at is called skip element. This is purely a string processing function and helps us parse a path name. It doesn't involve inodes at all. It's passed a pointer to a string containing a path name, such as this one right here, and it will identify the first file name in that path and advance the pointer to the second file name, and it will return a pointer to the second file name. It will also save the first file name, so the second argument is a pointer to a 14-byte area. Remember that file names can be at most 14 characters, and it will save the first component in that area. If there is no file name in the path, then it will return null. Okay, so let's take a look at the code here. One thing I want to mention is that it ignores leading slashes, and if there are multiple slashes separating the file names, then it ignores that and treats them just as one. Okay, so here we're passed a pointer to the path and a pointer to the 14-byte area to save the first file name. So it begins by skipping past any leading slashes and ignoring them. And then if there's nothing found, that is, if we're positioned at the null byte at the end of the string, then there is no file name in the path, so we just return 0. Now we're positioned at the beginning of the first file name, so we save a pointer to that. And in this while loop here, we advance our pointer to whatever comes after that file name. So we search for the next slash or the next null character and stop when we hit something, either of those. And at that point, we know where the first file name begins and where it ends, so we can compute its length. Now we're going to move it into this name area. Okay, that's our second argument here. And we need to check to see whether it's greater than 14, if it's 14 or greater than 14 bytes in length, then we don't need to worry about the null. We just move it into the name field, and directory size is this 14 constant. If it is 13 or fewer characters, we need to add a null character after the end of it. So here we do it that way. And finally, we advance the pointer to the next thing beyond the slashes. So if we ended pointing to a slash, then we advance to the second file name or the end of the string and return the pointer that results. Next, I want to look at the nameI function. This is sort of the culmination of all the functions we've been looking at. NameI is passed a pointer to a path, and it locates that file on disk and returns a pointer to the inode for that file. And if there's any problem, such as the file is not found or the path name is no good, then it returns null. The actual work is done by this nameX function. There's another function, nameI parent, which is very similar to nameI, except it stops one level earlier. And both the nameI and nameI parent call nameX to do the work. So let's take a look at nameI and nameI parent here. Okay, nameI calls nameX and nameI parent calls nameX, and the only difference is they pass a flag to say which is involved here. Now, nameX requires a 14-byte field, a 14-byte memory area in which to save each file name in the path. And so in the case of nameI parent, we're trying to extract that, so it's passed in. But for nameI, we have a local variable that's the 14-byte field, and we're passing in the address of that variable. Okay, so let's take a look at nameX. It is passed a pointer to the path, and then this flag, nameI parent. If this flag is 0, then we will return the inode for the parent, okay, and copy the final file name into the name area, okay. Otherwise, we will open that file directly. Okay, so this nameX is only called from nameI and nameI parent. So I think the way to look at this thing is to imagine we're calling it from name I first, and I'll look at the second case a bit later. But so imagine that this flag is 0, right? And we have a 14-byte area that we can use within this name X function. So here we start by seeing whether the path begins with a slash. If it does, then we need to start with the root directory. Okay, so here we have the device on which the file system is kept and the inode number, which is 1 for the root directory, and we just get a pointer to the inode for that here. And let's say we've got just a slash and nothing else. Then this while, okay, so here's a while loop that processes each element in the path name, but let's say that there's nothing. Then we immediately exit the loop, and we're assuming that this flag is 0, so we skip this, and we just return a pointer to the inode for the root. It doesn't lock it, but it does add it to the cache. So this flag is called, somewhat confusingly, name I parent, and so the flag is called name I parent, and we're going to assume that that is false when we look at this code here. Now, if it doesn't start with a slash, then we need to begin processing the path from the current working directory. So the structure for this particular process that we're running in has a field called current working directory, and that is a pointer to an inode. So that's the current working directory, and we need to use that. We haven't seen this idupe function before, but basically all this does is just increment the reference count for this inode. In fact, let me just stop and show you the code for that. Here's the idupe function. It's passed a pointer to an inode, and it acquires the spin lock for the cache, increments the reference count, and then releases the lock. Okay, so that's what idupe is doing right here. And iget will increase the reference count for the root directory. So regardless of whether we do this or we do this, we've got an inode that's been added to the cache, and we've incremented the reference count for that. So that's what will be true when we return down here. Okay, so whether we start with a slash or not, we are ready to start looking at the path. So we're going to call the skip element function that we just talked about to locate the first file name in the path and to advance the path pointer to the next element. So that's what happens here. Okay, if there is no next element, then we are done. Okay, and we exit the loop. But otherwise, we need to look in the directory that we're pointed to at the beginning of this for the file that has this name. So here we are identifying the name and saving it in this name variable. And at that point, the next thing we're going to do is call directory lookup. But before we do that, we need to lock that inode. Okay, so we lock it here, and then we call directory lookup. Before we do that, we make sure that the file that we are thinking is a directory is in fact a directory. So we check its type. And if it's not a directory, something is the matter. And so we are going to abort and return a 0 to indicate that we had problems. But remember that we've got the directory. It has been had its reference count increased, and we've locked it. So we need to undo both of those things. So we unlock it and decrease the reference count before we return. Now, I said let's just take a look at the case where this flag, this name I parent flag, is false. So let's skip that for now. And now we're ready to do the directory lookup. So we've got the first, or I should say the next file name in the path in this string here. And this is our inode of the directory. And so we're going to do a directory lookup. So remember that this is the offset into the directory. This is a pointer to a place where we can save the offset if we want to. We're going to pass in null because we don't care where in the directory this name is found. So we don't need that information. We pass in a null rather than the address of a variable in which to store it. So this is going to return a pointer to the inode for this file. So that's what the next inode is. And we'll see here we're going to advance to that. Okay, so if everything goes well, then we return a pointer to an inode, but if there's a problem, we return null. And again, we've got this directory that we're looking into locked, and we've increased its reference count. So we need to undo those two things and return a null indication to indicate that there was a problem. Okay, we couldn't find the file. So if there's a problem with the path name and we can't find one of the files in the path name, we consider it an error and return null. But assuming everything's okay, then we're done with this directory. We now have the next thing in the path name. Could be the file that we're looking for, that is the thing at the end of the path name, or it could be another directory. In other words, we could be looking at the bin directory, or we could be down here looking at the file that we want to get at. But in any case, we are going to advance to that. So we unlock the directory and then move to the next thing, the next file in the path, and then we loop back up. Okay, if that was it, okay, if that was the last thing in the path, then this thing is going to return 0, and we'll exit, and we'll exit the loop here and then return a pointer to the file that we found. Otherwise, the while loop will continue and look at the next element in the path name. Okay, so now let's take a look at the name I parent function. Here we're passing in 1, so in this case we just want to stop prematurely. So again, we start with something. Let's say we start with the root directory, and we set IP to point to the next directory or the next thing in the path. And let's say there's nothing else. Okay, this returns 0. Well, there is no second thing, and that's a problem. So if this thing is true, which it will be for a name I parent situation, then we've got a problem. We need to return 0. There was not at least one file name in the path. So we unlock the sorry, we haven't locked it because the lock occurs in the loop. Okay, we do not have IP locked at this point, so we don't need to unlock it. We just need to decrement its reference count before we return null. Okay, in the loop, what do we see? It's the same thing. We're going through it, and we get the next thing in the path. Okay, we look in the directory that is pointed to by IP and identify the next file. And if we are wanting to stop early and we've come to the end of the path, all right, we've advanced path to point to the thing after name, and if there is nothing after name, then we can stop. Okay, we're done. Okay, we've identified the last thing in the file, and IP at this point points to the directory. So we unlock the directory and return it. Okay, I think that's it for all the functions in the file fs.c. I will see you in the next video.